we can classify reactions into 7 fundamental reaction types, and you see those here. So the acid-base type involves swapping of hydrogen atoms from a basic group to an acidic group. Notice the similarity here between the acid and the base and the nucleophile-electrophile concept that I just talked about. So the base possesses a reactive pair of electrons that it donates to the acid, which is an electrophile, and the acid accepts the electrons from the HX bond. That's how the hydrogen atom gets transferred from the acid to the base. There we go. 2 and 3 are oxidation and reduction, and oxidation and reduction have to do with a trade of CH bonds for CX bonds. So we talk about the oxidation state of atoms as the charge an atom would have if we gave all of its electrons away to more electronegative atoms. So adding an X group onto a carbon increases the oxidation state of that carbon. As a result, we call that reaction an oxidation. On the other hand, replacing it with a hydrogen, which is a sort of neutral, unreactive ligand, is a reduction, because it's a reduction in the oxidation state of the carbon. Substitution is number 4, and that essentially replaces one group on carbon with another, and in the process kicks off the originally substituted group in the form of a leaving group. 5 and 6 are opposites of each other, elimination and addition. Elimination is the formation of a double bond or a pi bond with the cleavage of 2 single bonds. Addition, on the other hand, is the addition of a single bond across a pi bond. So with an addition reaction, the pi bond is broken and 2 new single bonds are formed. In an elimination reaction, the opposite takes place and 2 single bonds are broken to form a pi bond. The final kind of reaction is a rearrangement, which involves the isomerization or the formation of an isomer of the starting compound. Here's an example of a sigmatropic rearrangement down here at the bottom. And what you can see here is that the original starting molecule has been transformed from one kind of diene, one kind of dialkene, to a different kind of dialkene with the double bonds in a different position. So those 2 molecules are isomers, and that general kind of reaction type is called a rearrangement. Now, when we talk about these fundamental reaction types, we break them down even further into what are called mechanistic steps. Every mechanistic step of a reaction is a fundamental interaction between typically a nucleophile and an electrophile. So what you're looking at here is the mechanism of acid-catalyzed Fischer esterification, which converts a carboxylic acid into an ester. Every step of this process is an individual interaction between an individual nucleophile and an individual electrophile. And hopefully, as you study organic chemistry, you'll get used to identifying nucleophiles and electrophiles. That's a very important part of thinking about organic reactivity. So for instance, in the first step, the electrophile is clearly the proton, which is lacking any electrons at all. It's simply a bare proton. And the nucleophile is a lone pair on the oxygen atom. And so interactions of this type, where again we use that curved arrow to represent the flow of 2 electrons to form a new bond, are very, very common in organic chemistry. And mechanisms give you an immense amount of information about how a reaction actually proceeds. So even though in the laboratory you may only observe the very starting materials and the very final products of a reaction, say you only observe the acid and the carboxylic acid and the final ester, knowing something about the mechanism is critical when thinking about what starting materials and what products are going to work for that kind of reaction. I wanted to close with a few thoughts for next time. So we haven't said much so far about the orbital basis of reactivity. What is its basis in molecular orbital terms? And after studying Chapter 1 and the orbital properties of molecules on structural grounds, we can begin to think about the orbital basis of chemical change. What orbitals are involved in this transfer of electrons, and how does that work? How does that influence reactivity? And how do molecular orbitals add something to the conversation? I'd invite you to think about what electrons are the most reactive in molecules and why you might expect that to be the case. And then finally, how do bonds form in orbital terms? What kinds of concepts do we bring to the table to think about bonding on molecular orbital terms? So that's pretty much all I've got for you today. Thanks for joining us, and I'll see you next time.